Good day, everyone. I am Engineer Salvador Ricacho, and on behalf of Engineer Ryan Lee Ronquillo, Engineer James Alice, and our advisor, Assistant Professor Francis Eric Almaquer, I will be presenting our study titled Simple and Rapid Colorimetric Sensing of Nickel-2 Ions in Tap Water based on aggregation of citrate-stabilized silver nanoparticles. Nickel is one of the most abundant alloying elements in the production of engineered alloys. It is found in many day-to-day objects, as well as in many industrial items. It is used in jewelries, heat exchangers, ceramics, batteries, and valves, among many others. Due to its wide array of uses, nickel is a valuable resource. In recent years, mining and production of nickel in Southeast Asia have increased, with the Philippines as the top producer in the region. However, in April 2017, 28 out of 41 Philippine nickel mining companies were threatened to be shut down by the Mines and Geosciences Bureau. These mining companies were held responsible for leaving rivers, rice fields, and watersheds polluted with toxic red nickel laterite. Inevitably, nickel reaches our aquatic environment through seepage, spillage, mine tailings, and even by direct discharge. According to a study in 2018, one of the most common sources of human nickel exposure is by drinking water. Nickel, a heavy metal, when taken in large amounts, leads to lung damage, kidney damage, and defects in the central nervous system. Therefore, there is a need to detect contamination levels of nickel, especially to waters nearest to humans. However, current detection methods are expensive, are time-consuming, cannot be used in situ, and require special training to operate. Hence, there is a need to explore alternative methods that are simple, fast, and easy to use. Nanotechnology is an attractive alternative, especially nanosensors, which can measure and detect nanoscopic particles such as metal ions. Nanosensors offer simple operation and rapid results, are sensitive and selective, and are available for on-site applications. Nanosensors are composed of a nanoparticle and a stabilizing agent. A nanoparticle is usually a metallic nanoparticle. Silver is preferred over gold because it is more economic, and also it has excellent optical properties, making it a good nanosensor. Its stabilizing agent is a chemical stabilizer that provides stability and colorimetric sensing abilities to the nanoparticle. Previously reported nickel nanosensors used glutathione and N-acetylcysteine as stabilizing agents. However, these stabilizing agents were found to be toxic to cells, have complex and long synthesis methods involving hours of stirring and even overnight synthesis, and are relatively costly compared to other chemical stabilizers. For these reasons, we have conducted our study with the primary objective of detecting nickel in tap water samples using citrate stabilizer, a less expensive, less cytotoxic, and as a simple synthesis stabilizing agent for silver nanoparticles. Specifically, synthesize CTAGNP using chemical method and characterize using UV-Vis and TEM analysis. Investigate its colorimetric properties and detect nickel ions in tap water samples. For the synthesis method, a silver nitrate solution was added dropwise to a sodium borohydride solution under an ice bath and in constant stirring. Dropwise addition was continued until a yellow-colored solution was formed, indicating the formation of silver nanoparticles. Then, the trisodium citrate stabilizer was added to the solution. The resulting CTAGNP solution was then subjected to UV-Vis analysis and TEM analysis for characterization. For the colorimetric response test, different nickel concentrations were prepared and were added to the CTAGNP solution. The resulting solutions were subjected to image analysis, UV analysis, and the calibration curve was plotted to determine the relationship between increasing concentration and the changes in absorbance behavior. For the selectivity tests, different metal ion solutions of same concentration were prepared and were also added dropwise to the seed agent solution. The resulting solutions were also subjected to image analysis, UV-Vis analysis, and the relative response of these metal ions relative to nickel were determined. For the detection of nickel in tap water samples, different nickel concentrations were prepared using tap water. This piped tap water was added to the seed agent solution, and the resulting solutions were subjected to image analysis, and the percent difference between the prepared concentration and the detected concentration was determined. The characterization results show that for the image analysis, a bright yellow colored solution was formed. The UV-Vis analysis also show an absorbance peak at 392 nanometers. The peak width at half max, or the PWHM, which measures the width of the absorbance curve at half the maximum height, is 57.78 nanometers. According to the study of Solomon, the yellow color, the absorbance peak around 400 nanometers, and the value of the PWHM indicate the presence of well-dispersed silver nanoparticles. RTM analysis also confirmed the presence of small, quasi-spherical nanoparticles with an average particle size of 14.56 nanometers, indicating a successful synthesis of the seed agent P. For the colorimetric response tests, our image analysis showed that addition of increasing nickel concentrations from 0.6 millimolars to 1.6 millimolar produced recognizable color changes from yellow to deep orange within a minute after addition. The UV-Vis analysis also show a decrease in absorbance peak at 392 nanometers and the formation of a new peak at 510 nanometers. These changes in the absorbance curve was observed to be consistent with the color changes. RTM analysis also showed that the initially monodispersed silver nanoparticles, as shown above, aggregated after the addition of nickel, as shown below. The calibration curve that was plotted between the changes in the absorbance behavior at 510 nanometers and 392 nanometers versus increasing concentration showed a strong linearity from 0.7 to 1.6 millimolar. The limit of detection, or the LOD, was also calculated to be 0.75 millimolars, or around 44 milligrams per liter. The strong linearity, which has a coefficient of determination of 0.9958, shows a consistent behavior of our nanosensor for increasing concentrations. The LOD of the nanosensor, which is 44 milligrams per liter, was also found to be lower than the common nickel concentrations found in polluted municipal water supplies of 100 to 2,500 milligrams per liter. The changes in the color of the solution of the seed agent P can be explained by the property of the seed agent P called the localized surface plasmon resonance, or the LSPR. LSPR is the collective oscillations of the electrons surrounding the metal nanostructure. It gives the property of the nanoparticle to be yellow in solution and is highly dependent on the morphology or the size of the nanoparticles. With the presence of metal ions such as nickel, the morphology of the nanoparticle changes, and hence a color change in the solution is induced. From our results and from related literature, the sensing mechanism can be deduced. The citrate ion attached on the seed agent P has one free carboxyl arm and one free hydroxyl arm. These free arms act as ligands, or as binding agents, with the presence of nickel, leading to the formation of nickel carboxyl complexes. This formation of coordination complexes result to a decrease in interparticle distance, and hence a change in morphology, ultimately resulting to a change in color. For the selectivity study, our image analysis showed that only nickel among the different metal ions, lithium, magnesium, calcium, and silver, produced recognizable color change to the solution. The relative responses of these metal ions, as shown by the UV-Vis analysis, are significantly lower compared to nickel, only amounting to less than 35%. For the detection of nickel in tap water samples, our image analysis show a similar color response between the distilled water samples and the tap water samples. The The difference between the prepared concentration and the detected fecal concentration was also found to be only 15.78%. Statistical tests show that this percent difference is insignificant, implying that our assay is applicable to tap water samples. In conclusion, we have successfully synthesized ANP as a colorimetric sensor for nickel in tap water samples. For the future of this study, we will be focusing on improving the limit of detection and finally embedding the nanoparticles in paper to create paper sensors. We would like to acknowledge the contributions of the UPV, SBIRG, and the Nanotechnology Research Laboratory of the University of the Philippines, Diliman. That's all. Thank you for listening.